also uses the same programming method. And then there is the Yasnak control. It's a major Japanese manufacturer of controls. It uses the same basic programming system. Also Mitsubishi makes a control that's sold on many different machine tools that would use the same programming system. A reason that Fanuc is so strong in this field, they make a very nice and very reliable control. They also make their own feed motors. They make their own main motor. And so do many of these other people. As a group, the controls today are very, very reliable. So we'll get started with the programming for the 6T control. Let's make this part together here, and what it will be a program with very little differences that will apply to the 6T and also to the very modern OT control. What we'll do is we'll see this part made together, and then we'll actually see the part run. And let's take a closer look at the part first. Let's take a look at this part together here. First of all, notice that all the dimensions are laid out coming from our face, except for this chamfer dimension, and we'll do this together. Here, we want to go to 1 inch. We would like to feed up in this direction to this intersection point where this radius blends into this angle, and all these numbers have been figured out correctly. 1.374, 1.499, etc. Same in this direction. So what we would like to do here is we would like to achieve that this tool comes down about 100,000 away from here, and we will figure out what this point will be right here. And let's take a look at that. This is supposed to be a 100,000 by 45 degree chamfer. So if we stay 100,000 away from here in this direction, point 1 is the point to which we will wrap it. That means that this tangent point is dropped another 100,000 per side in the x direction. To begin with, the piece is 2.5, and if we take out off the 100,000 per side, then this actual dimension here would be 2.5 minus 2 times 0.1, or 2.3. Now there's another 100 here per side. That makes this here 2.1. So we will wrap it to 2.1 by 100. This dimension, of course, is the 100,000, so this dimension will be 0.1. Then we will be in cutter compensation when we get to here. We will feed to here. We will now feed from this point to here, and cutter comp will get us tangent to this angle. Then we will just feed straight up to this, and cutter comp will set the tool properly here. Then we'll cut a radius going around to here. We will then go straight to here, and then feed off our part to here, and we'll wrap it away. Now we'll go through the whole program together. When we're all done with writing this down, we will then see this program actually cut. Let's do that. The first thing we would have on the modern machines is that we have a program number 0300. The letter O followed by up to a 4-digit number. So 300 is fine either for the 6, the 10, the 0. It's the same for all of them. And what we usually have in our first line here, we would have a G50 code. It would look like this, G50. Now, on the 6, on the 10, we would then put in where this tool is sitting as a diameter value, just like we did on the 5T. Let's assume this is at 6, and in in this direction, this tool is sitting at 6 inches. That would be the distance from the finished face of our part. So we would show that by saying here that we're sitting at X 6.0 and Z 6.0. And in the same line today, there is a limiting speed, S 1500. Or whatever you put here would mean that during the cycle of this part, we do not want to run any faster than 1500 RPM. This is a limiting speed that's actuated by the G50 code. Now the difference would be that on the 6T, we are programming where this is located. And on the OT control, on this control, this is not necessary. Because this would be in something called coordinate system setting, where we actually dial it into our coordinate system. This method though will work on both. It will work on all controls. It will work on the 6, the 0, the 15, on all of them. But in order not to program it, we must have this option that's only on the OT control. So we just told it where this tool is located. And the next thing would be that we are going to tell it what tool we would like to use, T. And what we usually do, we put in this tool number, this O600. This would be the position on the turret without an offset assigned. We will assign this offset a little bit later. And later we will see how we change this. And into this same line, there could be a gear range. A machine typically, when it's very small, just runs straight off our DC main motor. But as it gets a little bit bigger, there might be a high and low gear range. This would be one of the gear ranges. The example later, we will see a gear range. Now, we're going to tell it how fast we would like to run. And we do it like this. This means we are programming this in constant surface feet. And this is the value of the surface feet. 650 would mean that we're asking this control to figure out its own RPM all the way through. Now as we start cutting on a larger diameter, we're going to hear it slow down. And as we go toward center, we would hear it and see it speed up. And also in this line, this would actually turn the spindle on. So right now, the control knows where the tool is. It knows what tool it is, and it knows how fast to run. And in the next line, we would tell it that we would like to wrap it somewhere, G0. And into this line, we tell it that we want to use cutter compensation. This means cutter comp to the right. We'll talk about that later. Cutter comp right and left. This means to the right. That as you're looking at this tool in the direction of its travel, looking from behind the tool, you would picture yourself looking from here. This tool is to the right of a workpiece. That's what G42 means, as opposed to G41, which would be left. And this is all set on the way now to this point right here, which is located at X 2.1 and Z 0.1. That is this point right here. And into this line, we also put the fact that as we're doing all this, we put in our tool offset and repeat our tool number, T0606. Now we're not going to be using coolant. This could also be the line where you actually turn your coolant on. So we're here now, and we have asked the control to look at the shape ahead of itself and figure out cutter compensation in this direction. Now we're going to start cutting by saying G1 to this point right here. And we just put the actual dimension in there of X 2.5 and Z minus 0.1. Remember that this goes with the upper line. So we're now in this position, but into this line right here, we need to put a feed rate. And the feed rate would depend on what kind of surface finish we're trying to achieve across here. And a combination spindle speed, feed rate, and the size of this tool would give us our surface finish. We are going to be feeding at approximately 10 thousandths per revolution, f.01. Now, notice, every number is written with a decimal point. Where before on the older control, we had to write all the numbers out in tenths. Here we don't have to. That's one of the advantages of this control, the newer controls. Here we have a program number, so we can have a whole number of programs in a library. We have decimal points all over. We have constant surface feet, and we have nose radius compensation, which means we don't have to figure out all these extra calculations. So we are now sitting in this position, and now all we would do here is we would say go to Z minus whatever this position is, and the control would figure out whatever is necessary to get a tangent to this angle. We would say 1. That's this, 1 inch, that's all. Now, angle going up. We have figured out these dimensions very carefully. This is the X dimension and this is the Z dimension. So here we're going to say go to X, 3.932. 3.932 and Z minus 1.374. Minus 1.374. What would happen now is that we feed up in this direction. Control would look ahead to this radius and make sure we're sitting in the right relationship to whatever is coming up. Now here's how we program this little radius. It's either a G2 or a G3. Now this would be a G3, counterclockwise. That goes to an X dimension and it goes to a Z dimension. The X dimension here is the part of 4. The Z dimension is 1.499. 1.499, and the radius itself is 0.25. The control will figure out whatever else is necessary to get it properly in cutter comp to this point up here. Now we have a straight line going back. That would be this line right here, G1. That goes back to Z minus 1.55, which is this wall back here. And now all we have to do is face straight up along this wall to a point larger than this OD. How about if we go to X 5.1, and we would be above this work part right now. Okay, we're finished. Now here's what we would have to do. On the OT, on the 6T. If this is the 6T control, we would say rapid, and we would say G40. And now, on the 6T control, we have to make sure we go back to where we came from. We go back to 6 and 6. And at the same time, we take off our tool offset by saying T0600. So we're canceling cutter comp. We're going back to 6 by 6. And now we're on the 6T control. We programmed our initial starting point. We're now going to be programming where we go back to. And on the OT control, we could really go back to any place we want to, because coordinate system setting will watch where we came from and where we're going. Outside of that, it's the same program. And we are finished. So in this last line right here, we could just say M30, which means end of program. And what would happen is it will go from here all the way back to the beginning, and we would be ready to run this part all over again. So what we have now is a combination of things in this little program. A typical program start. This is a typical program start. For any tool that we start, whenever we go to a tool change, we would have 4 blocks that would look like this. A G50 line, a tool line, a G96 line, and then going to the point where we want to do something. Then the cutting sequence itself would be, of course, dependent on what kind of part we're going to make. In the end, though, we would always go back to some point away, take out our tool offset, and if we're using cutter comp, we would take that out, and then we would just stop. Okay, there's a typical programming example for a 6T or an OT, and what we'll look at right now is we will look at an OT control actually cutting this part, and we will make some minor changes in that part. We'll probably change the tool offset in that part. Let's take a look what a finished cut would look like on this particular part here. What we'll do after this, we'll go and edit some of the values to change our feed rates, to speed up the surface feed, to try to improve the part and to use tool offsets, etc. This is a piece of mild steel, and we're running somewhere around 550 surface feet, and we'll speed that up in a little while. That whole sequence didn't take very long, and we'll check out how long it took, and then we'll see if we can improve it a little bit. On our position screen on this particular machine, there is an option that tells us how long the cycle time took. And in the lower right hand corner, you can see that it took 32 seconds to do this last sequence. And what we'll do is we'll change some of our values around and see if we can improve that a little bit. Now this was a finished cut, so it didn't take very long to begin with. We were already running quite fast. But let's see what our program looks like. Remember, in order to change anything at all, we have to be in the edit mode. Now we were running our part in the memory mode, which is the machine operation mode. So we have to switch over to edit right now. Okay, now we're in the edit mode. To get to the point where we'd like to edit, we use the cursor down button that steps through the values one step at a time. And then we will change our values by inputting a new value through the Alter, Insert, or Delete keys. Upper right hand side of the control. Now they could be in different positions on different controls, but basically you will always see an Alter and Insert Delete key. You will see a keyboard that would look a lot like this. You would see a cursor up and down. Below that is a page up and down that would change the whole page of your program. But what we'll do is we'll go through our values using the cursors and then change some of the values. Now this is the program that's just made this part. I'm in edit, and I will use my cursor to step through this program. I'm going cursor down right now. I first have to open the control lock switch. Then I step through it. The method is to step through one step at a time like I'm doing right now, or step through to a known value, but what I'll do right now is I'll go forward to our surface feet. And right now we're using 500 surface feet. I'll touch S650, alter. Open the key, alter that number. It is now 650. I'll go a little further forwards in our sequence. By the way, here's cutter compensation to the right. G42 is cutter compensation to the right. In the approach to the workpiece. It has to be in the approach to the workpiece. And I'll go forward to our feed rate. Here's F.01. I'll change that to F.012, which shows up on the left-hand side, and I'll hit alter. Now what I've done now is I've increased our service feet, and I've also increased our feed rate. And let's take a look at the same part again and see what difference that makes in our cycle time. Now, anytime you edit, you've got to make sure that you hit reset. That I'm doing this right now. The cursor has to go back to the head of the program. Now let's take a look and see what this looks like when we rerun it right now. In order to run right now, I have to get out of edit and switch over to memory. Also, right next to the edit key in this case is the lock. It's called Program Protect or Memory Protect. It's off right now. Some machines will run with it on or off. In this particular case, we have to go back to put the Memory Protect back to on. At the bottom of our program screen, there are a number of different buttons. There's one for program, current, next. The one that's most useful would be the program check screen. What that will do is it will show us a number of different things. It will show us 4 lines of our program. It will also show us our absolute dimensions, our distance to go. It will show us our spindle speed. It will show us a whole number of different things. So that's the one we usually end when we actually try a program. Now once you're running parts, it makes no difference, but when you're trying it, you'd like to see what's supposed to happen, and the distance to go here is very important. Let me give you an example of what the distance to go is really for. I'm stepping through our program right now. I'm in single block, so every time I hit start, it moves one line. It goes to the first G50 line, it reads the tool line, it will start to spindle right now. And in this line right now, coming up, is the line moving toward our work part. I let it go part way and then stop. Okay, I interrupted the cut. What I want to do is, I want to compare where we are to our distance to go screen. Now the distance to go says that in X, we have no distance to go, and in Z, there's about 1.3 inches to go. Now let's compare that to the position of our tool to our work part right now. In the X direction, I've reached the end of the travel and I'm near the tangent point of that little chamfer. But in the Z direction, I'm approximately 1.4 inches away or so from our part. Now my control tells me that it's going to move another 1.35, and visually I confirm that I've got approximately 1.5 inches to go. Now what you're supposed to do is this. You look at this and you say, does that make sense? And if it makes sense, what we can do is I can further reduce the rapid rate. I'll do that a little bit. I'll let it go a little closer and I'll shut it off again. Now I'm within 50 thousandths or so of the work part, and my distance to go tells me that I've got about 60 thousandths to go, so I'm fine. Now if right now the screen told me that it's going to move another inch, and I'm sitting right there, I better shut the machine off and start all over again and try to figure out what's wrong. So, properly done, you can be very, very safe using this type of machine. I'm going to take single block off right now and just let it run through the rest of the cycle.
Now I interrupted that last sequence by explaining something, so I let it run once more. Now I changed my tool offset a little bit so we see an extra little cut, and then we'll get a true indication of our cycle time. This is 100% feed rate, 100% rapid. Okay, let's take a look and see what that looks like. So there's our cycle time. It took 21 seconds as compared to, I believe last time it was about 32 seconds. So what you can do is by working properly with the surface feet, with tool life, and making changes that give you the proper surface finish, you can get your cycle time down substantially. If you put your mind to it, most parts can be made a whole lot faster.
The next thing we'll do is to look at a typical modern CNC machining center and a programming method for a machine like this. And the first thing we'll do is let's take a look at the tool change mechanism on this. This is what's called a simplified tool changer today. You notice there's a tool in the spindle and the station facing the spindle is open, because this type of changer will always put the tool away first before it rotates around and puts another tool into the spindle. We have a variety of tools. There's a face mill in the spindle, there's some drills, there's several boring bars, some tabs, some end mills. The way we would program this is to call for the tool number with an M code. It would say T1 M6 to actually change the tool. Many of the skills we talked about earlier, for instance, figuring out the RPM, figuring out the proper feed rate, would apply to a milling machine. This is a piece of aluminum, and we would have very high RPM, and it would be very important that we have the right feed rate, along with knowing that we normally use a 2-flute end mill for something like this. So let's take a look at a programming method for the modern CNC milling machine. First of all, let's take a look at the typical coordinate system. And this would apply to a very much older machining center, an older CNC mill like a Bridgeport with a control on it, and also a modern machine. That sideways is always called the X direction, and this is positive and this is negative. And in this direction, somewhere along our part, we decide where we want to start counting, and what we try to do is count from the lower left-hand side of our part, because then all our numbers will be positive in this direction. In and out is always called the Y direction. Numbers get larger, the numbers get smaller, and we do the same thing. We count from here because then everything inside a part is in a positive direction. And up and down on a milling machine is called the Z direction. And the numbers get bigger and the numbers get smaller. They get bigger away the further we travel away from our part, and the closer our tool gets to the top surface of our part, the smaller the numbers get. And what we try to do is we try to establish through tool length compensation that the top of our part will be Z0. So any dimension of a tool above our work part, let's say that this is a drill, and if this actual dimension is 1 inch, we would call that Z equals 1.0. Once we get down to here where we're actually touching our work part, this will be Z0, and anything that goes into our work part, like drilling a hole into our work part, would be